A lithium-ion battery is made up of four major parts: cathode, anode, electrolyte, and separator. You can think of your cathode and anode as your positive and negative terminals of the battery, and you're going to be exchanging lithium back and forth.
Imagine your phone, your car, even your home going up in flames, all because of a tiny battery. Every day, millions of lithium-ion batteries silently power the world around us. But what happens when they fail? Explosions, fires, and deadly consequences.
We have a lithium atom, which is within the anode structure, and it loses an electron to that anode structure, which then goes on to power our car. Well, since the lithium has lost an electron, it is now a lithium ion, and it travels through the separator to find a parking space within the cathode structure.
Just from something we take for granted. What started as a groundbreaking discovery in the 1970s has now turned into one of the most powerful and dangerous forces in modern technology. This is the hidden side of the batteries we can't live without, and it could be more dangerous than you ever imagined. Lithium-ion batteries have become one of the most widely used power sources in modern life. These small cylindrical powerhouses can be found in almost every device we rely on, from smartphones and laptops to electric cars and even satellites orbiting Earth. But despite their widespread use, lithium-ion batteries are built from some surprisingly simple materials and are often considered rudimentary in their design. At their core, a lithium-ion battery consists of just 2 meters of foil coated in a black paste, all packed into a tiny 45-gram cylinder. It's not exactly a cutting-edge appearance, yet these batteries power everything from household gadgets to the most advanced technology we use daily. But what makes them so powerful, and why do we still rely on them? Looking back to the 1980s, the world of rechargeable batteries was very different. Most batteries at that time had an energy density of just 40 to 60 watt-hours per kilogram. This meant that to power a 40-watt light bulb for an hour, you would need at least a kilogram of battery weight. As a result, when the first commercial mobile phone launched in 1983, its capabilities were fairly underwhelming by today's standards. It took 10 hours to charge the phone for just 30 minutes of talk time. Laptops, cameras, and even medical devices all faced similar limitations due to their bulky batteries. This problem caught the attention of major corporations, including electronics giants and oil companies. Everyone saw the potential for a breakthrough. If someone could figure out how to increase battery energy density even just slightly, it could spark a revolution in portable electronics, pushing us into a new era of digital technology. But what no one realized at the time was that the solution had already been discovered, albeit by a relatively unknown scientist. In 1972, Stanley Whittingham, a British chemist, was working at Exxon's research lab in New Jersey. Exxon, famously known as the world's largest oil company, was not a name you'd typically associate with battery development. However, the company had begun to explore alternative energy sources in response to the growing oil crisis of the early 1970s. The situation was grim. The United States had just backed Israel in the Arab-Israeli War, which led to Arab oil producers cutting off their exports. By the end of December 1973, the price of crude oil had doubled, causing widespread panic. The situation became even more dire as Americans waited in long queues at gas stations. As part of the government's response, the national speed limit was even lowered to 55 miles per hour to conserve fuel. In the face of rising oil costs and concerns over future shortages, Exxon began to take the possibility of electricity as an alternative energy source seriously. Although electric vehicles had been explored earlier in the century, they had always been limited by their batteries. In the early 1900s, the top-selling car was electric, surpassing steam and gasoline-powered vehicles in popularity. However, the electric cars of that time were hindered by their heavy batteries, which weighed as much as 360 kilograms and provided a range of only around 60 kilometers. Over time, the energy density of these batteries deteriorated further, leaving them unable to compete with gasoline-powered cars. By the mid-1920s, electric vehicles were all but obsolete. But now, with the oil crisis causing widespread panic, Exxon and other companies turned their focus back to the electric car, realizing that to make it viable, a better battery had to be found. This was the pivotal moment when Whittingham's research began to attract attention. Whittingham had been working on materials that could store large amounts of energy in a compact, lightweight form, which he believed could unlock the potential of electric vehicles. Whittingham's breakthrough came with his discovery of lithium's potential as a key component in rechargeable batteries. Unlike other metals, lithium has the unique ability to release more energy per electron than any other material used in batteries. Its small size and low density make it ideal for storing energy in a compact space, which is exactly what Whittingham needed to create a more efficient battery. But the road to success was far from smooth. The challenge, however, was that lithium's reactivity made it difficult to work with. Pure lithium is highly unstable, particularly when exposed to water. So, in order to use lithium in a battery, Whittingham needed to find a solution that could safely contain the metal. He turned to a solution of lithium salt in an organic solvent, which allowed lithium ions to shuttle between electrodes without breaking down the solvent. This new electrolyte allowed Whittingham to break through the previous limitations of battery chemistry, pushing the voltage of his prototype to 2.4 volts per cell, nearly double that of conventional batteries at the time. Whittingham's design was an early prototype of what is now known as the lithium-ion battery. It used a metallic lithium anode on one side, a titanium disulfide cathode on the other, and the newly developed electrolyte in between. When the circuit was closed, lithium atoms at the anode would give up their electrons, generating a current that powered any connected devices. Meanwhile, lithium ions would pass through a porous separator and move toward the cathode. The process could be reversed when the battery was recharged, making the battery reusable over multiple cycles. However, despite the breakthrough, Whittingham's battery was still far from perfect. The instability of lithium and the volatile electrolyte posed serious risks, and the battery's design was far too dangerous for widespread use. Exxon, which had initially invested heavily in Whittingham's research, began to lose interest as the oil crisis ended. The company's focus shifted back to its core business of oil, and the momentum for further development of the lithium-ion battery stalled. Whittingham's breakthrough did not immediately lead to the creation of the batteries that are now so familiar to us. His research had made it clear that lithium had the potential to revolutionize energy storage, but the challenges were far from over. The battery's instability, particularly the dangers posed by the lithium metal used in the anode, presented significant hurdles. While Whittingham had demonstrated that lithium could store energy more efficiently than any other material, the volatility of the battery's chemistry made it unsuitable for everyday use. At the time, Exxon, which had supported Whittingham's research, was under less pressure as the oil crisis eased. The company began to shift its focus back to its core business, oil, leaving the lithium battery project to languish. Though Whittingham had published his findings in 1976, the world was not yet ready for lithium-ion batteries. Without further investment or momentum, the first wave of lithium-ion research seemed to stall, and Whittingham's breakthrough fell into relative obscurity. However, Whittingham's pioneering work did not go unnoticed forever. A copy of his paper made its way to Oxford University in the UK, where it caught the attention of John B. Goodenough, an American physicist leading a solid-state chemistry group. Goodenough was no stranger to the challenges of battery chemistry. He had previously worked with transition metal oxides, compounds known for their stability and high electron affinity, properties that made them ideal for use in batteries. As Goodenough read Whittingham's paper, one thing immediately stood out to him: the cell voltage of Whittingham's prototype was limited by the titanium disulfide used as the cathode. Goodenough believed that by choosing a more efficient cathode material, he could unlock even more potential. Goodenough's insights led him to experiment with new cathode materials, and after some trials, he found success with lithium cobalt oxide. This compound was significantly more stable than the titanium disulfide Whittingham had used and allowed for a much higher voltage. Where Whittingham's battery had reached a maximum of 2.4 volts per cell, Goodenough's new design spiked to 4 volts per cell. This was a crucial breakthrough. It effectively doubled the voltage, which directly increased the battery's power. More importantly, Goodenough's new cathode had an additional advantage over Whittingham's original design. Lithium cobalt oxide already contained lithium ions within its structure, meaning it didn't require lithium metal at the anode. This solved one of the most dangerous aspects of Whittingham's battery, the highly reactive lithium metal. By using lithium cobalt oxide, Goodenough's removed the need for lithium metal altogether, making the design significantly safer. But even with this improvement, Goodenough's was not done. The next step was to find a suitable anode material that could complement the lithium cobalt oxide cathode. The anode in Whittingham's design had used lithium metal, which was both unstable and difficult to work with. Goodenough's needed an anode material that could interact with the lithium ions in a safe and efficient manner. After more research and experimentation, he settled on graphite as the ideal solution. Graphite, unlike lithium metal, was stable and capable of intercalating or absorbing lithium ions within its structure. Goodenough's combination of lithium cobalt oxide and graphite represented a significant leap forward in battery design. By using lithium cobalt oxide as the cathode and graphite as the anode, Goodenough's created a much safer, more efficient battery. The two materials worked in tandem, allowing lithium ions to move between them during charge and discharge cycles. This design had the added benefit of being much more durable and efficient than previous designs. The combination of lithium cobalt oxide and graphite not only provided a safer battery, but also made it possible to achieve higher energy density, meaning more power could be stored in a smaller, lighter package. However, even with this major breakthrough, commercialization of lithium-ion batteries was still some way off. At this point, Goodenough's had a working prototype, but no company seemed ready to invest in his design. He reached out to various battery manufacturers across the US, the UK, and Europe, hoping to find a partner willing to help bring the technology to market. But much to his frustration, no one was interested. Even though Goodenough's had created a battery with a far higher voltage and much greater stability, it was still a tough sell. In 1981, Goodenough's breakthrough design was patented by a government lab near Oxford, though Goodenough's himself received little financial compensation for his work. In the meantime, a new player was entering the field. While Goodenough's work on lithium cobalt oxide and graphite had proven effective, it was still a long way from mass production. A chemist named Akira Yoshino, based in Japan, was on a parallel path to develop a safer, more reliable lithium-ion battery. Yoshino, like Goodenough's, was looking for an alternative to lithium metal for the anode, but he took a slightly different approach. Yoshino's work focused on developing an anode material that could safely absorb and release lithium ions. After months of trials with various materials, he found success with a new form of carbon called polyacetylene. Polyacetylene is unique in that it can conduct electricity like a metal, despite being a plastic material. This was an important discovery, as it allowed Yoshino to replace the unstable lithium metal anode with a much safer, more stable material. The polyacetylene anode could absorb lithium ions during charging and release them during discharging, just as lithium metal had done in Whittingham's original design. Yoshino's design also addressed a crucial problem that Whittingham and Goodenough's had not solved: how to make the battery lightweight and energy-dense enough for practical use. Yoshino realized that polyacetylene's low density made it an excellent candidate for this role, and he combined it with Goodenough's lithium cobalt oxide cathode. After some refinement, Yoshino's prototype was a success. He had created a much safer, more efficient lithium-ion battery, free from the dangers of lithium metal, and with much higher energy density than anything before. However, Yoshino's breakthrough was just the beginning. While he had successfully created a safer, more practical battery, the technology needed a manufacturer who could mass produce it. Yoshino's employer, Asahi Chemical, was not a battery company, so Yoshino's next step was to find a partner who could help bring his design to market. In 1986, Yoshino sent his prototype to a small company in the United States called Battery Engineering, which specialized in assembling small batteries. With their help, Yoshino's prototype became a fully functional lithium-ion battery. 2 weeks later, Asahi Chemical sent their first batch of working lithium-ion batteries to Sony in Japan. Sony, impressed by the potential of Yoshino's design, recognized its commercial value. The company quickly began to refine the prototype, and in 1991, Sony released the first commercially available lithium-ion battery. This was a landmark moment in the history of batteries. For the first time, a small, lightweight, rechargeable battery had the energy density and safety needed to power portable devices like camcorders, laptops, and eventually mobile phones. Yoshino, Goodenough, and Whittingham had all played pivotal roles in the development of the lithium-ion battery. But their work wouldn't have reached fruition without the contributions of many others in the battery industry. The release of Sony's lithium-ion battery in 1991 marked the beginning of a revolution in portable energy storage. The battery became the gold standard for everything from personal electronics to electric vehicles. What had once been a niche technology had now become the foundation for modern society's increasing reliance on batteries. The release of the first commercially available lithium-ion battery by Sony in 1991 marked a major turning point in the history of portable energy storage. For the first time, a lightweight rechargeable battery with a high energy density could be used to power consumer electronics reliably. The compact and efficient lithium-ion battery was a game-changer, allowing devices like camcorders, laptops, and later mobile phones to become smaller, lighter, and longer-lasting. Sony's lithium-ion battery quickly became the go-to power source for a range of electronic devices. The success of this new battery technology led to a surge in interest from other manufacturers, who quickly began developing their own versions. Companies like Panasonic and Sanyo were among the first to follow Sony's lead, introducing their own lithium-ion batteries to the market. By the mid-1990s, lithium-ion batteries were no longer just a niche product, they were powering a wide variety of consumer electronics. One of the key factors that contributed to the rapid adoption of lithium-ion batteries was their performance. Not only did they offer significantly higher energy densities compared to older battery technologies, but they also had a much longer cycle life, meaning they could be charged and discharged hundreds, even thousands of times, without significant degradation. This made them ideal for use in portable devices, where battery life was a crucial consideration. The advantages of lithium-ion batteries didn't stop there. They were also much lighter and more compact than previous rechargeable batteries, which made them ideal for mobile applications. As the demand for smaller and more powerful devices grew, the need for a compact and efficient energy source became even more pressing. Lithium-ion batteries filled this gap perfectly, making them the power source of choice for the rapidly expanding portable electronics market. By the late 1990s and early 2000s, lithium-ion batteries were firmly established as the industry standard for consumer electronics. Mobile phones, in particular, saw a revolution in battery performance. As mobile phone technology evolved, so too did the batteries that powered them. Lithium-ion batteries allowed phones to become slimmer, lighter, and more powerful, while also extending their battery life. This contributed to the rapid growth of the mobile phone market, as consumers were increasingly able to rely on their devices for a range of tasks, from calling and texting to browsing the internet and playing games. The success of lithium-ion batteries in the consumer electronics market also paved the way for their adoption in other industries, particularly in electric vehicles. As the world became more focused on sustainability and reducing dependence on fossil fuels, electric vehicles (EVs) emerged as a viable alternative to gasoline-powered cars. However, the success of electric vehicles was closely tied to the development of reliable and efficient battery technology. Lithium-ion batteries, with their high energy density, long cycle life, and relatively compact size, proved to be the perfect fit for EVs. The automotive industry began to take notice of lithium-ion batteries as early as the mid-2000s. Companies like Tesla, which was founded in 2003, were quick to recognize the potential of lithium-ion batteries to power electric vehicles. Tesla's breakthrough came in 2008 with the launch of the Tesla Roadster, the first production electric vehicle to use lithium-ion batteries. This vehicle demonstrated the potential for electric cars to offer long ranges, fast charging times, and high performance, qualities that had previously been a challenge for electric vehicles. As the demand for electric vehicles grew, so did the need for more advanced lithium-ion battery technologies. Automakers, battery manufacturers, and researchers began working together to push the limits of battery performance. By improving the energy density and reducing the cost of production, they were able to make electric vehicles more affordable and practical for everyday consumers. By the 2010s, lithium-ion batteries had become the dominant energy source for electric vehicles, and this trend showed no signs of slowing down. While lithium-ion batteries have been instrumental in the rise of electric vehicles, they have also become a key component in renewable energy systems. As the world moves towards a more sustainable energy future, energy storage has become increasingly important. Lithium-ion batteries are being used to store renewable energy from sources like solar and wind, allowing excess energy to be stored and used when needed. This is particularly important for areas where renewable energy production can be intermittent, such as on cloudy days or during periods of low wind. Lithium-ion batteries provide a way to smooth out these fluctuations and ensure a stable energy supply. One of the most significant developments in this area has been the rise of large-scale battery storage systems. These systems use lithium-ion batteries to store energy on a much larger scale than individual consumer devices. In some cases, entire power plants have been built around lithium-ion battery storage, allowing energy companies to store vast amounts of electricity for later use. These systems are especially useful for managing the integration of renewable energy into the grid, as they can quickly release stored energy when demand spikes or when renewable energy production is low. Despite their success, lithium-ion batteries are not without their challenges. One of the most pressing concerns is the environmental impact of the materials used to produce them. Lithium, cobalt, and nickel, three key materials used in the production of lithium-ion batteries, are not only expensive to extract, but also come with significant environmental and ethical issues. Lithium mining, for example, requires large amounts of water, which can lead to water shortages in some areas. Cobalt mining, particularly in the Democratic Republic of Congo, has been linked to human rights abuses, including child labor and unsafe working conditions. As demand for lithium-ion batteries continues to rise, these issues are becoming more pressing. In response to these concerns, researchers and companies are working on ways to make lithium-ion batteries more sustainable. Efforts are being made to develop alternative materials that are less harmful to the environment and more abundant. For example, some researchers are exploring the use of sodium-ion batteries, which could offer similar performance to lithium-ion batteries without the environmental impact. Others are investigating new battery designs that use less cobalt or nickel, or that use recycled materials to reduce the need for mining. The demand for lithium-ion batteries is also increasing at an unprecedented rate. As the adoption of electric vehicles continues to grow, the need for batteries capable of powering these vehicles will only. By 2030, it is estimated that over 17 million tons of battery-grade materials will be required to meet global demand. This will put immense pressure on the supply chain for lithium, cobalt, and nickel, and could lead to increased costs and shortages. At the same time, the price of lithium-ion batteries has been steadily decreasing. Since the early 1990s, the price per kilowatt-hour of lithium-ion batteries has dropped by nearly 99%, from around $9,000 to just $100 today. This dramatic reduction in cost has been a key factor in making electric vehicles and renewable energy storage more affordable and accessible to consumers. As lithium-ion technology continues to improve, the future holds exciting possibilities. Advances in energy density, charging speed, and battery life are making batteries more powerful and more practical for a wider range of applications. In the coming years, we may see the emergence of even more efficient and sustainable battery technologies. As researchers continue to push the boundaries of what is possible, the story of lithium-ion batteries is far from over. While they have already revolutionized the way we live, work, and travel, their future potential is even greater. The continued development of lithium-ion technology will be crucial to the success of renewable energy, electric vehicles, and countless other industries. As we move towards a more sustainable, electrified future, lithium-ion technologies will continue to play a central role in powering the world.